This video is for AP Calculus. This is section 3.3, Rules for Derivatives. So we're going to quickly review the power rule, which is used for polynomials, such as f of x equals x to the nth power. Remember, the n, the power, gets moved down and multiplies whatever's in front, and then we decrease the exponent by 1. So the derivative of f of x is f prime of x, and the derivative of x to the nth power is nx times n minus 1. Is that lighting better? Okay. Let's look at number 1. We have a polynomial here. Now we have a fourth degree, but it's in the denominator, so it's actually the negative fourth degree, and we have another denominator. Here's a hint for you. Whenever you have polynomial with terms in the denominator, we want to move those up. Remember, when you move them up, x to the fourth power becomes x to the negative fourth power when you move it up, minus 3x to the negative third power. You want to do that first so that when you decrease the exponent, you're doing it correctly. Minus 1 over x to the first power becomes negative x to the negative first power, plus x to the first power plus 2. Looks like I ran into problem number 2 already. Okay, so we're going to take the derivative. I'm going to move out here because I was running out of room. Y equals, we take the negative 4, and we multiply it by what's in front. 4 times negative 4 is negative 16x to the, now we need to decrease the exponent by 1, so the x to the negative fifth power, because negative 4 minus 1 is negative 5. Now we take the negative 3 and multiply it to the minus 3 in front, which makes it positive 9x to the, decrease the exponent, makes it negative 4. Next term, take the 2, multiply in front, so we have plus 4x to the first power when you decrease that one. Now we're going to take the negative 1, multiply it in front. A negative 1 times a negative 1 is a positive 1. X to the decrease negative 1 minus 1 is negative 2. And we have a positive 1, multiply it in front is just 1, and the x goes away because x to the 0 power is 1, and our constant disappears. So we never leave these negative exponents as negative exponents, so we're going to adjust that and bring the x to the denominator. Okay, the minus 16, however, stays in the numerator, and the x to the positive fifth power will be in the denominator. Plus 9 in the numerator over x to the positive 4 in the denominator. This one's good, plus 4x plus 1 over positive x squared plus 1. Okay, so there's our derivative. Definitely ran into problem number 2's space, so I'm just going to do that. Okay, I'm going to rewrite number 2 as well. Y equals, I can bring the 3 in front as a 1/3, right? X squared. I think doing that is nice because then when you take your 2, you're multiplying by a coefficient in front, which becomes 2/3. So y prime equals 2/3 x to the first power when you decrease the exponent. Okay, number 3, we have a radical here. Remember how the square root is actually x to the 1/2 power? So when we bring it up, we have y equals 5x to the negative 1/2 power. You'll want to change all of the square roots to exponential form so that we can use our power rule. And then I just take the negative 1/2, multiply by the 5, so I have nice little arrows so we can follow our work. Y equals, y prime, excuse me, equals negative 5/2 x to the, now we're decreasing by 1, so we're doing negative 1/2 minus 2 over 2. Isn't 2 over 2 the same thing as 1? I chose 2 over 2 so that my denominators matched. So I get negative 3/2. Okay, now negative exponents aren't acceptable, so we'll move that to the denominator. Y prime equals negative 5 over 2 times x to the positive 3/2. Okay, standard rule is if it starts in a certain form and you're not asked for a different form, to convert back to the original form. For instance, if the story problem has decimals in it, then your answer would probably be decimals if it didn't work out perfectly. If your story problem starts with fractions, then you would have your answer in fraction form. Well, this problem started in radical form, and currently I'm in exponential form. So I'm going to convert to radical form. Y prime equals negative 5 over 2. Now remember, the index is the denominator, so the 2 in the denominator tells me it's a square root because 1/2 is the exponent for a square root, and x cubed. This cubed can be written inside or it can be written outside. Both are the same. Okay, so that's review of the power rule. Now we're going to move on to what's called the product rule. The product rule, you can see here, d dx means we're taking the derivative of some function u times some function w. So we have two functions being multiplied together. So here is the rule for the product rule. When we have two functions u and v, when we take the derivative, we get u, make sure you can tell the difference between u's and v's, u times v prime plus v times u prime. Okay, I have a little saying for that that helps me remember it. I say first d last. D last means I take the derivative of the last plus last d first. D first means I take the derivative of the first. So u and v, u is the first term, v is the second term. So first, I'm going to just write u as is, times d last, the derivative of v, see v prime right here, plus, we have a plus here, last, v was the second function, d first means the derivative of the first function, which was u, so in this case u prime. Okay, so here's number 4. Notice we have a 4th degree binomial times a, well, x to the negative times a monomial right here. So our first function is u, that 4th degree binomial is u, and our monomial here is v. So we're going to do f prime. This time it doesn't say y equals, it says f of x equals, so we should keep to the same function notation. F prime of x equals first, so I'm just going to take the first function, 5x to the 4th minus 3x times d last, which means I want the derivative of 6x to the negative 2. So I take my negative 2, I multiply by 6 in front, which gives me negative 12x, decrease the exponent, which gives me negative 3, plus last d first. So I'm going to go to the last term. The last term is 6x to the negative 2, and I just write it as is, times d first. D first means we're going to take the derivative of the first function. So I take the 4, times it by the 5, 20x, decrease the exponent, so it's now cubed. Now I have x to the first power, take the 1, times by negative 3, which becomes negative 3, and the x disappears. Okay, so this first d last plus last d first is a helpful tool for the product rule. Now let's go through and simplify these. Remember your exponent rules. When we distribute, the coefficients multiply. 5 times negative 12 multiplies to negative 60. When we multiply terms of the same base, their exponents add. So 4 plus negative 3 is x to the first power. Now we need to do negative 12x to the negative 3rd power times negative 3x. So the coefficients, we have negative 3 times negative 12, which is positive 36. And then we add the exponents for the x's, x to the first, plus a negative 3 would be x to the negative 2 power. Plus, over here we have 6x to the negative 2 times 20x cubed, so 6 times 20 is 120. X to the, if we add the exponents, we get x to the first power. 6x to the negative second power times negative 3. So 6 times negative 3 is negative 18. X to the negative 2. Okay, find your like terms. Let's see, we have some linears right here. So f, notice how I'm keeping my work vertical, and each time I'm carrying down f to the negative, or f prime, excuse me, of x. My like terms, I have negative 60x plus 120x, which gives me positive 60x. Then I have x to the negative second power, 36 of them minus 18 of them means a positive 18 of them. Now x to the negative 2, I could write x to the negative 2, but I'm going to move it down right now to x to the positive 2. As long as it's in the denominator, it becomes x to the positive 2. So that's the product rule. Let's try the product rule again. Number 5, product rule. Can we still see it? Firsty last plus lasty first. Here's our first u. Here's our last v. Okay, so the derivative of f of x, you should write f prime of x. You need to keep it an equation. It can't all of a sudden become an expression. F prime of x, first, d last. So first was x squared minus 3x times the derivative of the second. So x cubed's derivative is 3x squared, and negative 4's derivative actually is 0. Plus last d first. So we take the last function, x cubed minus 4, times the derivative of the first function. So the first is x squared minus 3x, so the derivative is 2x minus 3. Now again, we're just going to go through and simplify. 3x squared times x squared is 3x to the 4th. 3x squared times negative 3x is negative 9x cubed, plus, looks like we have a binomial times a binomial here. X cubed times 2x is 2x to the 4th. X cubed times negative 3 is negative 3x cubed. Negative 4 times 2x is negative 8x. And negative 4 times negative 3 is a positive 12. Find your like terms, starting with our highest power. F prime of x equals 3 of them plus 2 of them makes 5x to the 4th. Now x cubes, I have negative 9 minus 3 makes negative 12. X cubed minus 8x, and then a constant plus 12. There is the product rule completed. We have the derivative of f prime of x. Okay, so both of those are an example of the product rule when we have two factors being multiplied. Okay, next we're going to do the quotient rule, which is when they are being divided. Okay, the quotient rule, you can see here d dx means we're taking the derivative of u divided by v. Okay, so it goes like this. V times u prime minus u times v prime all over v squared. Now, I can't really remember those u's and v's very well, so I have a nice little saying again for this one. Now, there's two different ways you can say this. I think of Seven Dwarfs, hi-ho. You know how they said hi-ho? They sing that song about being hi-ho, highs and hoes. So it goes ho d high minus, oops, d high. Let me actually write high. Ho d high minus high d ho all over ho ho. That's how I have always had it memorized since high school. But some people don't say ho, some people say low. So I'll write the other one that actually will probably make more sense to you. Low d high minus high d low all over. Some people say low squared, some people say low low. Whatever works for you to memorize. Okay, you can use either one. I just out of habit always say hi-de-ho minus or oops, I just said it backwards. Ho-dee hi minus hi-dee ho over ho-ho. That's just always like just flowed right off my tongue. Ho-dee hi minus hi-dee ho over ho-ho. I remember in grad school I was talking to one of my statistics professors. I was in his office during office hours, and statistics you actually use a lot of calculus. So we were working on some calculus, and I was like, oh, is this the ho-dee hi minus hi-dee ho over ho-ho? And he looked at me and he's like, whatever it takes to remember it. I was like, okay, which I was correct, but he just had never heard that saying before. A lot of people do use this bottom one, low-dee high minus high-dee low over low-low or low squared. So take your pick. I usually slip and say this one, but I will try to say actually the low, okay, instead of saying ho. But the ho's represents the denominator, meaning the lowest function, u and v. V would be the lowest function. The high obviously represents the higher function. Okay, so we're going to take the derivative of 6 and 7. So the derivative of y would be y prime. Okay, so we're going to go, I'll try to do this one. Low-dee high. So we're going to write the low as is, which is x plus 2. D high, the derivative of the high, meaning the numerator. The derivative of 1 is just 0. Minus high, high is 1. D low, whenever it says D, that means you're taking the derivative of. The derivative of x plus 2 is just 1. All over low, low, or low squared, which is x plus 2 squared. Okay, so let's go through and simplify. Well, if we're multiplying by 0, that goes away. Negative 1 times 1 is just negative 1 over x plus 2 all squared. Okay, you can write it like that, or we could go through and put y prime equals negative 1 over, remember the song? First you square the first term, square the last one too. In between the first and last is first times last times 2. X times 2 times 2 makes 4x. That's acceptable, and I would also say that would be acceptable. Okay, so number 7, applying the quotient rule. Ho-dee high minus high-dee ho over ho-ho, or low-dee high minus high-dee low over low squared. Whichever rolls off your tongue the best, use that one. Okay, notice we're not in y equals notation, we're in f of x notation, so we're going to just say f prime of x when we take the derivative. F prime of x is low-dee high. So low, I just copy the low function, x squared minus 4. D high, derivative of the numerator, x plus 1, the derivative of x is 1. The derivative of a constant is 0, so we don't need to write anything. Minus high-dee low. So high is just the numerator, x plus 1, times the derivative of the denominator. The derivative of x squared is 2x. The derivative of minus 4 is 0. So we don't need to write anything for that. All over the derivative, or the denominator squared, low, low. X squared minus 4 all squared. Okay, some simplification. F prime of x equals, this binomial times by 1 is just the same binomial, x squared minus 4. Minus, here we have a little bit of distributive property, and then we'll have some like terms. X times 2x is 2x squared, plus 1 times 2x is 2x. All over x squared minus 4 squared. F prime of x equals, notice we have to distribute that in, so I'm actually going to have x squared minus 4 minus 2x squared, and then we distribute it in again, minus 2x, all over x squared minus 4, all squared. Okay, f prime of x equals, I have like terms right here and here. So 1x squared minus 2x squared makes negative x squared. And then we have only one linear term, minus 2x, and one constant, minus 4. Okay, then we have over x squared minus 4 all squared. So there is your simplified derivative for number 7. Okay, some things to keep track of. The product rule is plus. Think of a times sign, just kind of flipped is plus. And the quotient rule is subtraction. So the division bar is like a subtraction bar. Kind of looks like, horizontal line, horizontal line. Because some people mess those up. Some people put a plus when it should be minus, and some people put a minus when it should be plus. So multiplication looks like a plus sign if you just tilt it, right? And division looks like a subtraction sign. So quotient rule, subtract. Product rule, add. Okay? Continuing on. Okay, so number 8, if h of x equals f of x times g of x, ooh, that looks like a product rule to me, find dh dx. So this is saying we're going to take the derivative with respect to x of h of 2. Okay, notice h equals f of x times g of x. So we're also given these values on the side. Values for f of 2, f prime of 2, g of 2, and g prime of 2. So we're going to start with h of x equals f of x times g of x. We have our first and we have our last. We're going to do firsty last plus lasty first. So h prime of x equals first d last. The derivative of g is g prime of x. Getting used to doing problems that are like in this arbitrary form with no actual terms or numbers in is very important, because you will see a handful of problems that are in this arbitrary case that you still have to be able to apply these same rules to. So I have first d last, I have a prime sign there, plus last is g of x, d first. The derivative of f of x is f prime of x. Okay, now we don't just want h prime of x, we want to find h of 2, the derivative of h of 2. So this is going to become h prime of 2 equals f of 2 times g prime of 2 plus g of 2 times f prime of 2. And we actually know the values for all of these based off of the given information over here on the left. So we just go f of 2 is 3 times g prime of 2 right here is 2 plus g of 2 is 4 times f prime of 2 is negative 1. Notice I'm carrying down my notation. Everything's lined up. Okay, so I have 3 times 2 is 6 minus 4. So hence our answer. H prime of 2 equals 2. Okay, so, or in other words, the derivative of h with respect to x of 2 equals 2. That's the same. So what's in the denominator by that d is what we're taking the derivative with respect to. See, we were taking the derivative with respect to all of the x's, and the numerator here, d of h, tells you what function you are applying it to. Okay, let's try. And the directions say use all of these values given here on the left for numbers 8 through 10. So we can use those values for the next two. Okay, and we have this arbitrary case, number 9, with the quotient rule. F of x over g of x equals h of x. So we're going to do h prime of x equals ho-d high, or low-d high. So low is g of x. D high, the derivative of the numerator is f prime of x, minus high d low is f of x, times the derivative of the denominator, which is g of x, over ho-ho, or low, or you can call it low squared. So g of x squared. Now, the interesting place that you put the squared of this, it actually looks like this. You'll notice this with signs as well. We don't say sine of x all squared, we say sine squared x. So same thing here, same notation, g squared x. Now we need to go through and plug in the required value. We're evaluating when x is 2. So h prime of x, of 2 equals g of 2 f prime of 2 minus f of 2 g prime of 2 all over g squared of 2. Okay, well, we know those values. G of 2, come to your list up here. G of 2 was 4 times f prime of 2. F prime of 2 is negative 1 minus f of 2 was 3 times g prime of 2 was 2 all over g of 2 squared. G of 2 was 4 squared. Oops, you can't see that now. There you go. Okay, so just continuing with the work, we get negative 4 minus 6 over 16. Okay, negative 10 over 16 equals negative 5 over 8 is our h prime of 2. Again, that's the same thing. I ran out of room, so I'm going to put it over here. It's the same thing as saying dh dx of 2 equals negative 5/8. So dh dx of 2 is similar notation to h prime of 2. It means the same. Okay, number 10. That looks like a fun one. Let's see what we got here. The derivative of 3f minus 5g. Now 3f, that's just 3 times a function. Okay, so that means we have two different product rules going on. So let's see what that turns out to be. Where our first function is 3 and our second function is f. So when I take the derivative, yeah, and also this notation is a little different, right? Before they said dh dx of 2, and now they're saying take the derivative of this function at x equals 2. So the setup is slightly different. Okay, so first d last, first is 3, d last of f is f prime. Okay, in this case I'm going to add in an x because we're eventually going to have to plug in a 2. First d last plus last d first, f is last, d first. Well, what's the derivative of 3? The derivative of 3 is 0, so we'll see an interesting relationship that happens. Okay, first d last plus last d first. Okay, minus, we do the same thing for the 5g. First d last, first is 5, because I already put the minus sign out front, last is g. First d last is 5 times g prime of x plus last d first, g of x times the derivative of 5 is 0. Interesting. Those both cancel out, so we just get 3 f prime of x minus f g prime of x. So technically this is the product rule on this first term and this second term, but look what happens. Couldn't I just kind of ignore doing the product rule on the 3 and just do the derivative of the f prime, or of f, and we just get f prime of x times 3, and just kind of ignore doing the product rule in the negative 5 and do just the derivative of g, and g's derivative is g prime, and then just multiply it by a negative 5. When you have these multipliers, they just pop out front. You don't really have to apply the derivative to them, but you can see if you do apply the quotient rule, it just becomes a 0 because of taking the derivative of a constant. Okay, so now we're going to evaluate at x equaling 2. 3 times f prime of 2 minus 5 times g prime of 2. We know f prime of 2. We come up to our little chart here. Can you still see that? There we go. F prime of 2 equals negative 1, so it's 3 times negative 1. Minus 5 times g prime of 2 is 2. Okay, so 3 times negative 1 is negative 3, minus 10, and we have negative 13. Okay. So, yes, number 10 had product rule. That's why it's included. But just as a reminder, if we have a multiplier times a function, You don't really have to apply the quotient rule or the product rule to the multiplier. You just make sure you multiply the 3 times the derivative of the function, and in this case the -5 times the derivative of the function. Okay, one last problem. Given f of x equals this quadratic, find the tangent line, ooh, parallel to the x-axis. Important stuff here. Well, when we find the tangent line, first, what are we looking for when we're looking for a tangent line? And it needs to be parallel to the x-axis. Interesting. Well, we know this is a quadratic. Okay, we know a quadratic is like a parabola shape. If I plugged in a 0 in for the x's, I'd have y equals -6. Oops, so -6 is down here. It's an upward parabola. I can factor that and actually find, excuse me, the x-intercept, so I'm not going to do that right now. But if we're parallel to the x-axis, well, the x-axis is, let me get a color here. The x-axis is horizontal like that, right? What point on the quadratic is going to have a parallel tangent line? And that point would have to be the maximum or the minimum, right? And since this is a positive x squared, we have a concave up, so hence we have to find the minimum point there. So our slope we're looking for, since it's a flat line, the slope of, or m, of the tangent line, I always like to mark a little TL so I know I'm finding the slope of the tangent line is 0. So number 2, step 2, how do we find the slope? Well, we know through calculus that the slope is the derivative of the function, and we can find the slope at any point of the function as long as it's differentiable there by taking the derivative. F prime of x is the derivative of f of x. Now this is just a power function, so we can easily take the derivative of it. X squared, bring the 2 in front, decrease the exponent, so the derivative is 2x. The derivative of minus x is just -1. Okay? So this allows us to find the slope at any point in the original parent function by plugging in our 0. F prime of x represents the slope. So f prime of x, we want the slope to be 0, equals 2x minus 1. So it's going to allow us to find the x value at which our slope is 0. So we just do a little solving, add your 1 over, you still see all that? And we get 1 equals 2x. Divide by your 2, divide by your 2. So we'll have the slope of 0 when x equals 1/2. Okay, so when x equals 1/2, we have the slope of the tangent line equals 0. But that's not the answer. The answer comes from step 4. Plug in the x and to get you, oops, I'm running into my thing, to get you the point. Once you have the point, use our point slope form. Okay, we have the x. Now we're going to plug x into the original function, so we have the y, which creates a point. X is 1/2, so I'm going to plug in 1/2 wherever there is an x, including in the f of x. 1/2 squared minus 1/2 minus 6. So 1/2 squared is 1/4 minus 1/2 minus 6. So common denominators to make that 2/4. 1/4 minus 2/4 is -1/4 minus 6. Okay, so if we have -1/4 minus, let's see, to make a common denominator times by 4, so we get 24/4, and we have -25/4. This is the y value when x is 1/2. So it's not the prettiest point ever, but here we go. This is the point we're going to plug in. And remember, when you have a point and you have a slope, you can write the equation for the line, and you don't have to simplify it. You can just plug it in and you can stop. So step 5, well, is plug in to the formula. Remember, y minus y1. So y is negative 25 over 4. So that would be positive 25 over 4 equals our slope, which is 0, times x minus 1/2. It was, minus 1/2. Now, technically, you can stop there. Timesing by 0 is a little funny, but you don't want to lose points by simplifying. If that's what it asks you for, you can stop there. If you really want to, you could go through and solve and get y equals negative 25 fourths, because this would cancel out to 0, and I move the 25 fourths over. Yes, you could solve, but I'm telling you, you can just stop. You don't have to simplify that. Plug it in and stop. And that is the end of our notes.